Have you ever wondered if your state's DMV has enough license plates to cover all of the cars that are operating on the road? Probably not. Did you recently turn 18, take up poker, and wonder how many ways there are to get a full house on a 5-card draw from a 52-card deck? Maybe. Did you lose the combination to a lock and wonder if it is worth your while to keep the lock and try and figure out the combination? Who hasn't? You can answer these questions and many more with a mathematic concept called counting. Check it out, and at the end of the video, I'll give you my answer to one of these questions.
You have 2 shirts and 3 pants. How many outfits are there? This is the multiplication principle, or the fundamental counting principle. It's the same principle but different ways of referring to it. And in this case, we simply are going to look at how many spots there are to fill and how many ways there are to fill each spot. So the spots are shirts and pants, and there's 2 ways for a shirt and there's 3 ways for pants, so that's a total of 6. If I said my shirts are blue and green and my pants are brown, black, and green, then the way that would be listed out is that I'd have black shirt, brown pants, black shirt, black pants, black shirt, green pants, and then I could have green shirt, brown pants, green shirt, black pants, or maybe I said blue pants, I don't know, black or blue, and then green shirt, green pants. So I could list out the 6 ways like that, but this counts it without listing them out. The next problem here, I have a 6-character license plate. 6 characters in a license plate. How many possibilities are there for a license plate if these constraints are met here? That the first character has to be one of the 26 letters of the alphabet. The second letter has to be one of the 26 characters of the alphabet. The third is one of the 26 letters. And then the 4th, 5th, and 6th characters of the license plate are from the numbers, from the digits, 0 through 9. So I've got 6 possible characters. And again, it's the multiplication principle. How many ways are there to fill each position? So I can have 26 letters, 26 letters, 26 letters, and then there's 10 possibilities for each of the digits. And you just multiply this, and that'll give you the total number of license plates that are possible. Here we have 2 operations. You can think about this as when you first learned, well, what does this mean? If you look down at the bottom here, what does that mean? And you learned what a radical meant and how to calculate that. So this is an operation, just like a radical or a logarithm or an exponent. And how do we calculate it? This one here, this P stands for permutation, and you're going to have a number and then the P and then another number. So N and R represent the 2 numbers that you're going to have there. And the calculation is going to be a factorial. So this is going to be 5 factorial, because this is the N, the number that goes in the numerator. And then you're going to have in the denominator, in this case, it'll be 5 minus 4 factorial. 5 factorial is 5 times 4 times 3 times 2 times 1. That's how factorials work. And then 5 minus 4 is going to be 1 factorial, which is 1. So I can just put a 1 there, right? And then we would just multiply those out, 20, 60, 120. This next one is a combination. So this C stands for combination. And this operation means that I'm going to do the first number is going to be the numerator, factorial. So I'm going to have 10 factorial in the numerator. And then in the denominator, I'm going to have 10 minus 7 factorial, and then 7 factorial. Now the 10 is 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Don't really need the 1, right? And then 10 minus 7, that's 3 factorial, which is 3 times 2 times 1. And then 7 factorial is 7, 6, 5, 4, 3, 2, 1. So this 7, 6, 5, 4, 3, 2, 1 cancels with this 7, 6, 5, 4, 3, 2, 1. And then this 3 I can cancel with a 3 for the 9. This 2 I can cancel with a 2 for the 8. And that's going to be 10 times 3 times 4, which will be 12 times 10 is 120. So those are just two operations, and we'll look at how those apply to what we've been looking at already in this one here. Here I'm going to choose 3 colors without replacement from 4 colors. So I'm going to choose 3 of these colors here. Red, blue, green, and purple. I'm going to choose 3 of them. How many ways are there to choose 3? So I could list them out, right? I could say, well, I'm going to choose red, blue, green. I could choose red, blue, purple. I could choose red, green, purple. I could choose blue, and then green, purple. And a question that we're going to have on a problem like this is what if I do blue, red, green? So notice here I did red, blue, green, and here I did blue, red, green. So I've got the same 3 colors, I've just written them in a different order. And does that matter? Well, the answer is in the question. It said if order is relevant. So this is saying that order is relevant. Okay? Now, I'm not going to keep listing these out because I have a way of counting them that doesn't force me to list them out. And that way of counting them is from these operations here. So these operations here are what count or help me to count in this situation. And the way it works is that I'm going to be choosing 4 from 4 colors, and I'm choosing 3 of them. And then because the order is relevant, I'm going to use the P. If order is not relevant, and let's just skip down to B here. How many ways are there to do this if order is not relevant? Then I'm going to have my 4 and my 3, and I'm going to choose the C. So if I'm counting, I'm selecting from a group of a group of items, and I want to see how many ways are there for me to select from that group. I look at if order is relevant, I'm going to use P, the permutation, and if order is not relevant, I'm going to use C, the combination. And then we just have our formula from the previous page. So this is going to be 4 factorial over 1 factorial. This one's going to be 4 factorial over 1 factorial, 3 factorial. And I'm not going to take time to evaluate those now, but you can look at the previous page. How do we evaluate these factorial expressions? Okay, now here's one. We're going to be choosing permutation or combination again. I've got 15 cities, and you want to visit, but can only visit 4. How many schedules are possible? So how many ways are there to visit 4 of the 15 cities? So that's 15, 4, and is it a permutation or a combination? I suppose you could make an argument that order matters, but we're going to say that order doesn't matter in this case. You're going to get to your 4 cities, and it doesn't matter what order you do it in. So because order does not matter, if we go back here, we see that if order is not relevant, we use the C. We use the combination. So let's go back here, and I'm going to do 15C4, and then I just plug into the formula like I did on the prior page there, like this, and we can evaluate that. This is also, you can also find, in addition to using the formula to get to the factorials here, you can also just key this into the calculator. Any scientific calculator will have a key in for combination and for permutation. And that's what we have here. Here we've got 34 salespeople. How many ways are there to rank the top 3? So this ranking, that's key, because now we're going to say order matters. So if I choose whatever, Bob, Mike, and Alice, so if I go Bob, Mike, and Alice, that's going to be different if I go Bob, Alice, Mike, because I'm ranking them. So here on this one, Mike is second and Alice is third, and on this one, Alice is second and Mike is third. So in that case, order is relevant, and when order is relevant, I'm going to use permutation. So how many ways are there to choose 3 of 34? It's going to be a permutation. And that'll be 35 factorial over 31 factorial. And again, there is a calculator key in for this. You can just key this into a calculator if you can find that operation.
Okay, as promised, I'm going to take one of those questions from the beginning of the video and talk about my answer to it. I just want to take the combination log problem. 40 times 40 times 40, 64,000. I figure about 15 seconds to try each combination. That's going to be 4 combinations a minute, and that there's 64,000, that's going to take about 16,000 minutes. Divided by 60 is going to be about 270 hours. That'd be an interesting endeavor to try and figure that out. But the real challenge would be keeping track of every combination that you've already tried. So I'm going to say buy a new lock.